Hello student, good morning. I am Dr. Ajay Kumar Sinha, Professor of Chemistry. Today I will continue from the last class. I was discussing crystal field theory, CFT, crystal field theory, and I have discussed crystal field splitting in octahedral coordination entities. Now I will continue. I was discussing about spectrochemical series. Spectrochemical series question is asked. In general, ligands can be arranged in a series in the order of increasing field strength. That I am telling you. First is iodide ion. Last class I have discussed. Again I am repeating. I will continue. Then I will come to the splitting in octahedral coordination complex. Then again I am repeating a spectrochemical series, that it is arranged in the order of increasing field strength. Every ligand has field strength. Then iodide ion is less than bromide ion. Bromide ion is less than thiocyanide SCN 1 minus, and that is less than chloride. And chloride is less than sulfide S2 minus, and S2 minus is less than fluoride, and fluoride is less than OH minus hydroxyl ion, and that is less than oxalate, means C2O4 2 minus, and C2O4 2 minus is less than H2O, and H2O is less than NCS 1 minus, and NCS 1 minus is less than EDTA 4 minus, and EDTA 4 minus is less than ammonia, means NH3, and NH3 is less than EN, means ethane 1,2-diamine, and EN is less than cyanide CN 1 minus, and CN 1 minus is less than carbonyl CO. Okay, this is the actually arrangement in the order of increasing field strength. Such a series is called a spectrochemical series. It is an experimentally determined series based on absorption of light by complexes with different ligands. Here I am telling you important point here. It is an experimentally determined series. How it was determined? Then it is experimentally determined series based on the absorption of light by complexes with different ligands. Different ligand will absorb different amount of light. Okay, based on the absorption of light by complexes with different ligands. Now just you consider electrons in the d orbitals of metal ion. Now just we should consider that things. D orbitals of metal ion in octahedral coordination entities. The single d electrons occur in one of the lower energy T2g orbitals. In octahedral cases, I am telling you. The single d electrons occupies one of the lower energy T2G orbitals. In D2 and D3 coordination entities. Here, listen carefully. The single d electrons occupies one of the lower energy T2G orbitals. In D2 and D3 coordination entities, the d electrons occupy the T2G orbitals singly in accordance with the Hund's rule. Means obviously in T2G 3 orbitals are there, then one by one it will fill. It will start filling according to the Hund's rule. 1, 1, 1. After that it will go up. Okay. And condition is also there. Sometimes only in this T2G it can accommodate also. It can paired only there. That is also possibilities. Then now first to think 1 electron, if 3 electrons are there, means D2, D3, D1, you have seen D1 means only first orbital it will go. T2G first orbital. D2 means 2 orbitals. D3 means 3 orbitals, 1 electron. All believe in the T2G orbitals, singly in accordance with Hund's rule. Now see here, for D4 ions, two possible patterns of electron distributions arises. First, in the fourth electron can either enter the T2G orbital level and pair with the existing electron. This is the first condition. Two actually patterns of electron distribution arises. First, the fourth electron could either enter the T2G level and pair with an existing electron. Or second possibility is it could avoid paying the price of pairing energy by occupying the Iitjee level. First, it can accommodate only T2G, fourth one. But now second option is there, second possibility is there, that it can go, means a higher energy level. Okay, it can go higher energy level, means Iitjee level. Okay, then this is the actually second possibilities. Then it could avoid paying the price of pairing energy by occupying the Iitjee level. The first possibility that it will go to the first, fourth one will either it will be paired, and if not, then it will go to the higher energy level. Higher energy level means in Iitjee. Okay, then two possibilities that first possibility, the fourth electron could either enter the T2G level and pair with an existing electron. There it can pair, first condition. And second, it could avoid paying the price of pairing energy by coupling the Iitjee level. Okay, which of these possibilities occur depends on the relative magnitude of the crystal field splitting. Actually, for pairing, extra energy is required. Remember, for the pairing, extra energy is required. Okay, that's why it may go to the Iitjee also. This remember, and this for pairing, that is the pairing energy is required for pairing. Okay, and that's why it can avoid paying the price of pairing energy by occupying the Iitjee level. Iitjee means higher energy level it can go. fourth one. Now this where it will go actually, whether it will go to the this T2G or Eeg, fourth electron, that depends. Which of these possibilities occur depends on the relative magnitude of crystal field splitting. That is the delta O. Delta O, O means octahedral, and the pairing energy, that is represented by P. Pairing energy is represented by capital P. Okay, then this it depends upon the magnitude of crystal field splitting and the pairing energy. P represents the energy required for electron pairing in a single orbital. These two options are, now condition you remember, question is asked. If delta O means crystal field splitting energy, magnitude of the crystal field splitting, then delta O. If delta O is less than P, first condition is that two options are there. If delta O is less than P, the fourth electron enters one of the Eeg orbitals, because delta G, delta O is less, energy of the delta O is less than P. That's why it will go to the Eeg orbitals, giving the configuration. What configuration it will give? Then T3 2G and Eeg1, means 3 electron will be in 2G and 1 electron will go to the Eeg orbital, total 4. Ligands for which delta O is less than P are known as weak field ligands and form high spin complexes. This is important point. What is actually weak ligands? Then ligands for which delta O is less than P, pairing energy, delta O, that is the crystal field splitting energy, if it is less than pairing energy, then ligands for which delta O is less than P are known as weak field ligands. It creates weak field and form high spin complexes, means unpaired electron. Complex will have unpaired electron, single electron. Now second, reverse of this, if delta O is greater than P, means splitting energy, crystal field splitting energy is more than P, then obviously electron will prefer T2G, lower energy only. If delta O octahedral is greater than P, it becomes more energetically favorable for the fourth electron to occupy a T2G orbitals with configuration T2G4 and Eeg is equal to 0. It will not go now in 0 because delta O value is greater than P. Hence it will remain only in the Eeg. It will be paired because delta O is more than P. That's why it becomes more energetically favorable for the fourth electron to occupy a T2G orbital with configuration T2G4 and Eeg 0. Eeg 0. This is the configuration. T2G 4 and Eeg is equal to Eeg have 0. Eeg 0 ligands. Okay. Means electron be arranged like that. 3 will be in the down. Not all 4 will be in the down, and upside no electron will be there in higher or vitals. Ligands which produce this effect are known as a strong field. Here the ligands which produce this effect means that pairing effect. Ligands which produce this effect means a pairing effect are known as a strong field ligands and form low spin complexes. Means it will not unpaired, it will be paired. Okay. Then this I told you a strong field ligand, it will make it paired. Okay, and it is called low spin complexes, or even you can say spin is there, then that means unpaired, then that will be in that complex it will be very very less, maybe 1 or 2 hardly, but here in a high spin number of unpaired electrons will be more, 3, 4, 5 like that way. Okay, and here high spin means more unpaired, and low spin complex means generally it will be paired, or if unpaired then very less, maybe 1 or 2 hardly. Then this I have told these two conditions, which ligand will with this will pair the electron and which will not pair the electron. Then this pairing of electron depends upon the ligands. Okay, a strong ligand and weak ligands. A strong weak field ligands and ligands which will prefer to go up, means high energy level, then that will be called weak field ligands, and it will form high spin complexes because it will form unpaired electron. And second case, that is field is that ligand will create a strong field ligand because it can pair the electron, and when it will pair, then now unpaired electron will be very very less. Generally it will be fully paired. Sometimes maybe 1 unpaired, 2 unpaired electron. Now I am going ahead. Calculation. If you calculate all the things, energy calculations show that D4 to D7, D4 now means D5, D6, D7, D4 to D7 coordination entities means complex are more stable for a strong field as compared to weak field. Just remember, D4 to D7 coordination entities are more stable for a strong field as compared to weak field gases. Okay. Now I am going to discuss crystal field splitting in tetrahedral coordination complex or entities. Here again situation will be splitting will be same way, but only it will reverse. All things will be the same. Only now this T2G which was down, it will go up, and up will come down, means Eeg will come down. Only this will reverse. What was in octahedral cases, in tetrahedral splitting will be reversed. it will reverse. Okay, in tetrahedral, splitting will be just opposite of octahedral. It will reverse. In tetrahedral coordination entities, formation, the d orbital splitting is inverted and is smaller as compared to octahedral field splitting. Okay, this in tetrahedral coordination entity formation means tetrahedral coordination complex formation, the d orbital splitting is inverted and is smaller as compared to the octahedral field splitting. For the same metal, the same ligand and metal ligand distance, three conditions are there for the same metal, for the same ligands and metal ligand distances. It is shown that delta T means here tetrahedral, delta T means tetrahedral. Now its value is less, different, 4/9 of delta O. Delta O, or you can tell this is the relation between delta T and delta O. Then delta T is related with delta O. How? Then delta T is equal to 4/9 of delta O. Means delta T is equal to 4/9 into delta O. Or you can write in another way also, delta T upon delta O is equal to 4/9. Delta T upon delta O is equal to 4/9. Its value is what? 4/9 means how much? That its value can calculate 4/9 means it will come point 4 point something will come. Okay, 4/9, then 40, then 90 to 4, 36. It will be less than 5. Okay, 0.456 like this it will come. Okay. Then this is the relation, because 4/9 you just to remember. Delta T is equal to 4/9 into delta O. Consequently, the orbital splitting energy are not sufficiently large. This value is not very large. Okay, splitting, this is actually called orbital splitting energy are not sufficiently large for forcing pairing, and therefore low spin configurations are rarely observed. Okay, here you listen carefully, because this value is not very large, 4/9. The orbital splitting energies are not sufficiently large for forcing pairing. It can't force. That's why low spin configurations are rarely observed, means less possibilities, very less possibilities. Okay, low spin means pairing is not possible, because splitting energy is less, hence it can't pair. Okay, then possibility is very less. Low spin configurations are rarely observed, because it can't paired. Okay, pairing is difficult here, because in splitting energies are not sufficiently large for forcing pairing, and therefore low spin configurations are rarely observed. Okay, it will be not paired. It will be high spin only. It will be high spin. In tetrahedral, electron will be high spin, means unpaired will be more. Okay, low spin will be less, rarely. Then here again you can understand by diagram also, same way that x-axis energy you can take increasing energy, and down d orbitals splitting you can take. Then d orbitals, 5 orbitals are there, then 5 closely line you can write, 5 very closely, because energy levels are same, almost same. And after that, after getting energy, before splitting, its energy will be more. That is called average energy of the d orbitals in a spherical crystal field. Average energy. Okay, average energy of the d orbitals in a spherical crystal field. And in third step, splitting will take place. Splitting will take place, splitting of d orbitals in tetrahedral crystal field. Then 3 orbitals will go up. Its energy will be now 2 by 5 more, 2 by 5 delta T. It is in octahedral 2 by 5 was less, down. Now this 2 by 5 will be up. dxy, dyz, tzx means T2g will go up, and energy will be 2 by 5 delta T. 2 by 5 delta T. T means tetrahedral, and down will be 3 by 5 delta T. Okay, and both if you will add, then 2 by 5 plus 3 by 5, it will be 1. Okay, then this value you remember, that in tetrahedral complex, in case of tetrahedral splitting, that it will be reverse of octahedral. Value will also reverse. 2 by 5 will be for T2G, and 3 by 5 will be for, this will be for Iitjee. Okay, then in T2G means dxy, dyz, dzx, and Iitjee means now dx square dash y square and dz square. 2 orbitals are there. Okay, now I am telling about important things which this ligand, this BBT was unable to explain. That is the color in coordination compounds. This was not discussed in BBT. It was the weakness of valence bond theory. Here you will get explanation. In crystal field theory, express colors in coordination compounds. I am explaining now that one of the most distinctive properties of transition metal complexes is their wide range of colors. Complex compounds have a wide range of colors. They have many colors. They are found in many colors. This is a very, very, you can tell, distinctive properties. Distinctive properties of transition metals complexes, that they have, means complexes have a wide range of colors. This means that some of the visible spectrum is being removed. This means that, here you understand, this means that some of the visible spectrum, 7 colors are there, in visible spectrum. Then here in this case that some of the visible spectrum is being removed from the white light. Here color, why they are giving color, there that explanation now you try to understand. Wide range of colors means that some of the visible spectrum is being removed from the white light as it passes through the sample. So the light that emerges is no longer white, because from white spectrum was absorbed. Now from the white light spectrum absorbed. Okay. Then obviously one will be less in the white light. White light that is the from the visual spectrum is being removed from the white light as it passes through the sample. So the light that emerges is no longer white. The color of the complex is complementary to that which is absorbed. Complementary to that which is absorbed. The complementary color is the color generated from the wavelength left over. After means from the white light you minus the spectrum, then one spectrum is less. Then remaining white light, what is the color? Sorry for interruption. I was discussing about the color. The color of complex is complementary to that which is observed, which is absorbed. The complementary color is the color generated from the wavelength left over. It is generated from the wavelength left over. If green light is absorbed by the complex, then remaining light it will, or complementary color will be red. It appears red. Again you understand, the complementary color is the color generated from the wavelength left over. Was some you can say wavelength absorbed, then remaining wavelength. The complementary color is the color generated from the wavelength left over. If green light is absorbed, then by the complex, if green light is absorbed by the complex, it appears red. Now this is important. Green light is absorbed, but that complex is now appearing red, remaining I can say wavelength, its color is red. Green absorbed, but you are seeing red. Complex will appear red. Okay. Then relationship of the different wavelength absorbed and the color observed, now I am telling you. Then every complex are absorbing different wavelength and complementary color will be different. Then example of first complex, cobalt Cl NH3 whole 5 2 plus. Cobalt Cl NH3 whole 5 2 plus. It absorbs wavelength of the light absorbed, I am telling you nanometer, nm. Then 535 this nanometer it absorbed. 535 nanometer it absorbed, and color of the light absorbed was yellow. 535 wavelength absorbed was 535 that nanometer, and color of the light absorbed was yellow, but now color of the coordination complex will be violet. Now see, yellow absorbed and violet it is appearing, complex is appearing violet. Then this is in the case of cobalt, one chloride ion is there, NH3 whole 5, 2 plus. Then these absorption, which light it will absorb, that depends upon ligands. What type of ligands are there in the complex. Now second example, now cobalt, 5 ammonia is there. Now in the place of chloride you can tell H2O is there, 1 H2O. Chloride is not there, in this case H2O is there, and outside 3 plus is there. This is the complex, cobalt NH3 whole 5 H2O, 1 H2O, outside 3 plus. In this complex absorbs 500 nanometer. Its wavelength is 500. Wavelength of the light absorbed is 500 nanometer. And 500 nanometer means blue-green. Color light absorbed is blue-green. Absorbed. Blue-green. And this color of the coordination compound will be, in this case, red. Color of the complex ion is red. Now see, blue-green absorbed, but it is appearing, complex is appearing red. And now third example I am telling you. Now in this case, only ammonia is there, cobalt ammonia 6, total 6. In the second case, it was 5 ammonia, 1 H2O. In the first case, it was 1 chloride and 5 ammonia. Now, all are ammonia. Cobalt NH3 whole 6 is there. Outside 3 plus. Here, it absorbs 475. And its wavelength is 475 nanometer. And 475 means blue. Every wavelength have fixed color. You remember it. You have seen 535 in the beginning, yellow color. 500 blue-green. Now 475 blue. See, 475 and 500 both are close. 535 was also somewhat close. 535. Then I am telling 500. Then now it is 475. Then 500 means blue-green. But now 475 means blue. Color of the light absorbed blue, because 475 wavelength, 475 nanometer wavelength means light absorbed is blue. And complementary color means what concept complex will show the color, that will be yellow orange. You have to remember it. All color, complementary color, you have to remember both absorbed and absorbed wavelength and color, and complementary color you have to remember. Okay, there is no technique to remember. You have to remember it. Okay. Then now next example I am telling you. Now ligand is changing. Cobalt cyanide whole 6, 3 minus is there. This absorbed 310 nanometer. Wavelength is becoming less. Less means more energy. Wavelength becoming less means more energy. Remember it. Wavelength is more means less energy. Just inversely. Okay, energy and wavelength are related inversely. More the wavelength, less the energy. Less the wavelength, more the energy. Frequency and energy are directly related. Frequency and energies are directly related, but energy and wavelengths are inversely related. Then now 310. This complex cobalt cyanide whole 6 3 minus, it absorbs 310 wavelength in a nanometer. That is coming under the, because more energy, ultraviolet. It is now entered in the ultraviolet. Color of the light absorbed is ultraviolet. And ultraviolet is not coming under the visible region. UV light is not coming, not in the visible region. UV light, ultraviolet light is not in the visible region, but it has absorbed. Then what will be now complementary for ultraviolet? Then it will be pale yellow, light yellow, you can tell, pale yellow. Now next example I am telling for copper H2O whole 4, Cu H2O whole 4, 2 plus. This is now for copper. Continuously I told for cobalt, and fourth one was with cyanide, 6 cyanide. Now it is copper, Cu H2O whole 4, 2 plus. It absorbs 600 nanometer. Now see, it is a frequency is more, not frequency, wavelength is more, 600, wavelength is more. Then wavelength is more means energy will be less, 600 nanometer. It is going to be absorbed. Then its color is red. 600 means red. Red color is going to be absorbed. Then now complex will appear blue. Red is going to be absorbed, and then complex will appear blue. Complementary color is blue. Now one more example I am telling you. Titanium H2O whole 6, titanium H2O whole 6, 3 plus. Complex is 3 plus. Titanium H2O whole 6, 6 molecules of water is attached. It will absorb 498. Its wavelength is 498. Okay, and its color is blue green. Its color is blue green. See, 498 and 500. I have discussed second compound. It absorbs 500. Then 500 means blue green. Now titanium H2O whole 6, it is 498. Then 500 and 498, what is the difference? Very less, negligible. Then its color is also blue green, same. 500 and 498 color absorbed is same, blue green. And then obviously when it is absorbing blue color, blue green, in both cases blue green, 500 and 498, then blue green is absorbing, then complementary color will be what? Violet. In this case it will be violet complementary color. This I have given some examples of complex ion. The color in the coordination compounds can be readily explained in terms of the crystal field theory. Consider, for example, the complex titanium H2O whole 6 3 plus, which is violet in color. This is an octahedral complex. Why? Because titanium has 6 H2O. This titanium complex has 6 H2O, 6 ligand of H2O. 6 bonds are there. Then here, just to understand, this complex is octahedral complex where the single electron titanium 3 plus is a 3d1 system. In this complex, only one in a d orbital, only one electron is there. That is called 3d1 system. Same may be possible d2 system, d3 system, d4 system, but here titanium 3 plus in this complex is a 3d1 system, only one electron is there. In the metal d orbital is in the T2G or level. Obviously, because only one electron is there in d, then where it will go? This electron will be present in T2G level in the ground state of the complex. Normal state or ground state, both are same. Then this one electron will be in the T2G level in the ground state of the complex. That's why it required, it absorbed only 498. Okay. Now further you understand, the next higher state available for the electron is the empty Iitjee level. After the T2G level, where it will go? Electron, it will go to the Iitjee level, higher energy. The next higher state available for the electron is the empty Iitjee level, high energy. If light corresponding to the energy of blue-green region is absorbed by the complex, it would excite the electron from T2G level to the Iitjee level. This is the important. Now, if more energetic light of more energy, if light corresponding to the energy of blue-green region is absorbed by the complex, it would excite the electron from T2G level to Iitjee level, from T2G to the Iitjee level, because Iitjee level has less energy. T2 and Iitjee is more energy level. Then electron, after getting the excitation, by getting the energy, T2G electron will be excited and it will go to the higher energy level, that is the Iitjee. Means T2G1 EX, that is the in ground state. D1 was only one electron, then that was in 2G, T2G1, and in Iitjee that time in the beginning 0 electron. But now after excitation, that electron will go to the Iitjee. Means now in T2G it will be 0 electron and Iitjee will have 1 electron. This is the excitation. After the excitation, means T2G1, Iitjee 0. Now it will become T2G 0 and Iitjee will be 1. Now in T2G, no electron. Whatever electron was there, that went to Iitjee. Iitjee electron now have 1 electron. Consequently, the complex appears violet in color. Okay, because now it is in higher. It went to the higher. Complementary color for blue-green is violet. The crystal field theory attributes the color of the coordination compounds to DD transition of the electron. How they are explaining this crystal field theory for the color? Then its main reason is that DD transition of electron from the one energy level of T, it will go to the other energy level, from one D to the other D, from Iitjee to, from T2G to Iitjee. Means DD transition, that is called in shortcut D transition of the electron. Because in going more energy will be required. Then what type of energy what type of frequency it absorbed? more if you want to send it higher energy level, then more more energy will be required. The more energy means what? Frequency will be what? This wavelength and frequency has, you can say, inverse, inverse relation. If wavelength is more, frequency will be less. Less energy means, less frequency means more energy. Okay, wavelength and frequency as inwardly related, inwardly, reverse way. Then if wavelength is more, it means frequency will be less. Frequency will be less, and less frequency means more energy. Okay, this you remember that wavelength and energy is inversely related. If frequency is wavelength is more, frequency will be less. Okay, then here during transformation from lower energy to higher energy, that frequency will change. Okay, because it requires more energy. Then after getting the energy, electron will go from the low d orbitals to the high d orbitals. Means from T to G to, it will go to the Iitjee. Okay, and because more energy is required, then what type of frequency is absorbed, accordingly it will show the color. Complementary color will be accordingly. Okay, then ground state, how will you represent ground state? Ground state and normal state both are same. Then T to G, 3 orbitals you can represent just like a 3 line. In VVT you have given a round for one orbital. Okay, for the orbital you have given a round. As for example, for Px, Py, Pz, 3 round you have given for 3 orbitals. For D, 5 round you have given circle for the 5 orbitals. Okay, and for S only 1 orbital, only 1 round for S orbital. But here in T to G, but here in crystal field theory, you will write one line for 1 orbital, because they consider point charge. Crystal field theory considers point charge. Then only here representation for orbital is just like a one line, a small line. Then 3 line you can draw. For T to G orbital, 3 orbitals are there. Then 3 line giving some gap you can write. 1 line, again little gap. Second line, again little gap. And third line, just like in VBT circle we are writing, then all circle little gap was there, like that way. Then here that in one orbital only 1 electron is there, D1 in ground state. Then after getting higher energy, then now upside 2 orbitals are there, means 2 line you can draw for Iitjee 2 line you can draw. For 2 orbitals 2 line you can draw, and its energy is more and its line will be little more. Okay, or almost same you can write, no problem. But you are writing upside, energy gap is there, ground state and higher energy gap is there, energy level gap is there. Then because it is higher energy, then 2 line is there. 2 line means Iitjee, 2 Iitjee orbital. Then now in ground state only 1 electron is there, and after getting energy, means in excited state, this 1 electron will go to the higher energy level, means Iitjee. It will transfer from ground state to the can say higher energy level, means T2G 1 electron was there, that will go to the Iitjee orbital. Okay, Then this is the representation, that first you write 3 line down and 2 line up in the ground state, and again in excited state now 3 line you write and 2 line upside, but now in this 3 line no electron is there, because in the excited state electron, whatever one electron was there, it went to the up. Then in excited state, just like in VVT excited state you were writing the orbitals, like same way here in excited state you have to write the orbitals same way, 3 line down 2 line up, but only difference that in a ground state, now in ground state it was 1 electron, now here no electron, it went to the higher in Iitjee. Okay, this is the representation. It is important to note that in the absence of ligand, crystal field splitting does not occur. Just to remember a very, very important point, that in the absence of ligand, crystal field splitting does not occur, and hence the substance is colorless. If ligand is not there, substance will be colorless. Okay, ligand is responsible for color, for development of color. Ligand is responsible. If no ligand, then complex will be or compound will be colorless. Okay, crystal field splitting does not occur, and hence the substance is colorless. For the splitting, ligand is required. For example, removal of water from titanium H2O whole 6, outside 3 plus was there, then 3 chloride may come. Full coordination compound is titanium H2O whole 6 in a square bracket, outside Cl3. Now on heating renders it colorless. It will turn to colorless. Okay, titanium H2O whole 6 Cl3 on heating renders it colorless. It will become colorless because no H2O is there. No H2O. That's why now it will become, it was colored, now it become colorless because H2O was removed. Similarly, anhydrous copper sulfate CuSO4 is white. Copper sulfate and anhydrous. Copper sulfate always will be hydrated. Some water molecules will be absorbed. But if no H2O is absorbed, then copper sulfate will be what? Copper sulfate will be colorless. Okay, copper sulfate is colorless, white. You can tell that anhydrous copper sulfate is white, but copper sulfate 5H2O is blue in color. Copper sulfate 5H2O is blue in color. The influence of the ligand on the color of a complex may be illustrated by considering nickel H2O whole 6 2 minus complex. Already I told you, but again further can be illustrated by considering the nickel H2O whole 6 2 plus complex, which forms when nickel second chloride is dissolved in water. Okay, now I will tell you, if the didentate ligand ethane 1,2-diamine is progressively added in the molar ratio En, that is a nickel and this 1:1, 2:1, 3:1. If ratio is in 1:1, 2:1, 3:1, then you will find a different reaction and it will give different color. As for example, nickel H2O whole 6 nickel NiH2O whole 6 2 plus En plus En. En means 1,2-dimethyl 1,2-diamine 1,2-diamine, that is called En. Then NiH2O whole 6 2 plus En. Then En have you can say it is a didented and H2O 6 H2O is there. Then 2 will be replaced, 2 H2O will go outside and 1 En will come inside. Then compound, actually in the beginning nickel H2O whole 6 2 plus was green. Now after absorbing 1 En, now its color became pale blue. From green it became pale blue, means NiH2O whole 4 and 1 En entered. NiH2O whole 4 En outside 2 plus in aqueous solution. This is relation is in aqueous. Then now its color is pale blue. Then see, 2 H2O went outside and 1 En entered. 1 En means it is didented equal to 2 H2O, 2 ligand, because it is didented. Now again you can see from this complex pale blue where 1 En is there. Now suppose now 4 H2O was there. Suppose now again another En is entering. Then 2 H2O has to go outside. Then now pale blue, now it will become blue or purple. Pale blue, now it becomes purple or blue or purple, you can tell. And new complex will be NiH2O whole 2 and En whole 2. En whole 2 outside 2 plus. En is a neutral, that you know. It will not affect the charge. That's why always a complex ion will have 2 plus. Then now you can see blue, pale blue, now it became purple or blue purple, you can tell. Now again you can say this complex color will change. Again if one more En will enter, means all H2O will go out. Then now this blue pale color, now it will come violet, means NiH2O whole 2 En whole 2 plus in aqueous solution. Now suppose one more En is entering, then 3 En is entering, and this H2O 2 H2O is there, that is going outside. Then now new complex will be nickel En whole 3. Nickel En whole 3 outside 2 plus in aqueous solution. Then now this complex, new complex will be violet. Then see how you can see color changed. As the H2O went outside and its place En came, color began to change. In the beginning NiH2O whole 6 was green became pale blue when 2 H2O went and its place 1 En came. Now again this pale blue became blue or purple when 2 more H2O went outside and its place 1 more En came. And now in third case, both what was the remaining H2O, that also went and 1 more En came. Then now this time it became violet, means NiEn whole 3 2 plus, that is the violet. Okay. Then this I have discussed about the, I can say, complex formation. Then here important thing is there, for DD transition of electron, energy is required, and for the energy, to get the energy, light is required, and for the light, each light frequency, each spectrum has a fixed, spectrum has a fixed light color. Each spectrum is each spectrum has a fixed color. Every spectrum have a definite color. Correct? Then complementary color always you will get. What light absorbed, complementary color, complex color will be of complete, you can say complementary color of the light absorbed. Okay. Then this I discussed. Then here important is that light must be there. To show the colored compound, first DD transition is must, and for that ligands must approach. Without ligand, no splitting. Without ligands, no splitting, and for the splitting, DD transition of electron is required, and for that purpose, actually when ligands will approach, that time only light will be absorbed. Then light will be absorbed. Then what type of light absorbed? Complementary color you will get, because each spectrum has a definite color. Now I will tell, you can say, color of some gemstone. Gemstone you might have seen, ring in the finger. Many person you might have seen wearing a stone ring in the fingers, different color. Then I will give few examples. That is called gemstone. GEM, gemstone. Okay. The colors produced by electronic transition within the d orbitals of a transition metal ion occurs frequently in everyday life. Ruby is the name of the gemstone. RUBY, ruby. Ruby is a aluminum oxide. Ruby is a chemical name, you can understand. Al2O3, aluminum oxide, containing about, in this aluminum oxide or aluminum oxides contains about 0.5 to 1% chromium 3 plus ions. This aluminum oxide have less amount of chromium ions mixed in aluminum oxide. Chromium 3 plus is there. 3 plus means D3 electron. It has 3 D electron, which are randomly distributed in positions normally occupied by aluminum 3 plus. Aluminum 3 plus constitution is there. In that chromium is also there, and it has D3 electron. Aluminum is also Al3 plus. Then these chromium 3 plus ions are randomly distributed in positions normally occupied by aluminum 3 plus. Which along with the aluminum 3 plus, chromium ion will be randomly distributed in positions normally occupied by aluminum. Means where aluminum ions are there sometimes this will also go. Chromium 3 plus will go. Now after that what will happen? This chromium 3 species here, now after because it is mixed with aluminum 3 plus, in their position chromium is also there. Chromium 3 plus means D3 ions. We may view these chromium third species as octahedral chromium third complex. These D3 will form or forms chromium third species as octahedral chromium complex incorporated into the alumina lattice, means Al2O3. DD transition at these entities give rise to color. Because they are forming complex compound. Okay, means chromium third complex it will form. Chromium third complex it will form, because aluminum is also there. Aluminum is 3 plus state, and chromium is also 3 plus state. Then this chromium forms octahedral chromium third complex. It forms in the alumina lattice, and their DD transition at these centers gives rise to color. In chromium 3 plus, DD transition will take place. That's why it will appear colored. Okay. And ruby is common, you might have seen. This gemstone was found in marble from one country is there, Mogok. That is in Myanmar, place is there, Myanmar. There this ruby is found. And one more, emerald. You might have heard the name, gemstone emerald. This gemstone was found in Mujo, Colombia. In Mujo, place name is Mujo, and in Colombia is the country. Okay. Then in emerald, what happens? In emerald, chromium 3 plus ions occupy octahedral sites in the mineral beryl. One mineral is there, beryl, means a beryllium, compound of beryllium, Be3Al2Si6O18. This is the mineral. Then here also chromium 3 plus is found. Chromium 3 plus is here also found. This occupies, chromium 3 plus ion occupies octahedral sites in the mineral beryl. The absorption of bands seen in the ruby shift to lower wavelength. Lower wavelength means what? High energy, namely yellow red to blue. Yellow red to blue, that is the ruby, causing emerald to transmit light in the green region. Means complementary color of yellow red. Here this ruby and emerald, I am telling you, both are the gemstone. The absorption of bands seen in the ruby shift. In the ruby particularly, there what happens, already told you, DD transition, that I am telling you, the absorption band seen in the ruby shift to lower wavelength, longer wavelength. Longer wavelength means less energy. Longer wavelength means less energy, namely yellow, red and blue. Yellow, red and blue, causing emerald to transmit light in the green region. Means they are absorbing yellow, red and blue, they will absorb. And this light, coming light means transmit light, means complementary color will be green region. It will show green region, it will appear green. Okay, and reddish will be somewhat this ruby. It will look like a little brownish type, reddish brown. Okay, then here I told you that what happens in gem of emerald and ruby. Okay, there will be DD transition. Then a longer wavelength light, which is yellow, red and blue. Okay, these will cause, they will absorb yellow red in ruby and blue in emerald, causing emerald to transmit light in the green region. Okay, this I have discussed about the these things. DD transition is color of complex ion. Okay. Now limitation of crystal field theory I am telling you. Limitation. Okay, just like valence bond theory has limitation, now crystal field theory also have CFT. Crystal field theory is also has some limitation. CFT, that is called limitation of CFT, weakness of CFT, shortcomings of CFT. Okay, or somewhat failure, not fully. Failure means partially, not full. The crystal field model is successful in explaining the formation structure. Crystal field model is successful in explaining the formation, structure, color, and magnetic properties of coordination compounds to a large extent. However, now come to the weakness. However, from the assumptions that the ligands are point charges, it follows that anionic ligands should exert the greatest splitting effect because they consider ligand as a point charge. It follows that anionic ligands should exert the greatest splitting effect because they have negative charge. Anion means negative charge. The anionic ligands actually are found in the low end of the spectrochemical series. Anionic, according to crystal field theory, charge, these ligands are point charge. Then it follows that anionic ligand should exert the greatest splitting effect because it has negative charge. The anionic ligands actually are found at the low end of the spectrochemical series. But in spectrochemical series, it is found at the low end of energy. The anionic ligands actually are found at the low end of the spectrochemical series. First point. Okay. Means what it was considering as that it will give more splitting effect due to the energy or repulsion. But now that anionic ligands are actually found at the low end of the spectrochemical series. That is the first weakness. Second, further, it does not take into account the covalent character of bonding between the ligand and central metal atom. That, according to the crystal field theory, they are ionic. They have considered ionic because point charge. Okay, positive central is positively charged and ion is negatively. Correct? But that it was ionic, but they have not considered it. This theory does not take into account the covalent character of bonding. For the covalent character of the bonding between the ligand and the central metal atom, this theory does not tell. This is the second limitation. And third, there are some of the weakness of CFT which are explained by ligand field theory. Actually, its weakness, crystal field theory weakness is again explained by the ligand field theory, LFT, and molecular orbital theory. Okay, but at your level means up to medical and engineering, this is beyond the scope of the present study. In medical engineering, that is not here. MOT and this, it is for higher study. Molecular orbital theory and ligand field theory. Then now I have discussed weakness of crystal field theory. Now I am stopping only here. Next class I will discuss bonding in metal carbonyls and stability of coordination compounds. I will discuss in the next class. Thank you.